Okay, hello everybody. Welcome back from last week's break. This week is the final session that we'll have with Chongmin. We'll be covering the last topic of neural networks and deep learning, um, which is graph neural networks. And just to give you a bit of introduction to graph neural networks and why this is the last topic, it is because even for me, when I was learning deep learning and neural networks last year, graph neural networks wasn't a thing. It was very new, and it is starting to become prominent. So I will let Chongmin explain more about what graph neural networks is. Please take it away.
Yeah, hi. So thanks for the introduction. So today's topic is graph neural networks. Just to check, can you all hear me properly? And my screen is okay? All right, so graph neural networks have been quite useful in recent years because there are some kinds of data that are in the form of a graph. So before I move to those data, I just want to ask, like, any of you all heard of stuff like AlphaFold, the DeepMind protein folding neural network? Any of you heard of that? Okay, so AlphaFold uses a form of graph neural networks to model the interaction between proteins or the amino acids. Okay, there are other forms of graph neural networks. Okay, just think about it. Okay, what in your life is a graph? Okay, so this leads me to the next slide. A lot of the things that we model in our real lives are all graphs. Okay, so you take a look at this thing on the left here. You see these nodes here: purple nodes, green nodes, blue nodes, red nodes. Okay, so this might be something like a social network. Maybe you have yourself connected to some friends of like different types. Okay, maybe blue is like males, red is females, that kind of thing. Yeah. So this could be like a part of a social graph that we want to analyze like more in detail about like each individual person. Okay, and then these connections that this person has with other people can be quite important. Okay, think of Facebook. Okay, who my friends are also tell a bit of my own personality. Like if I'm friends with all the bodybuilders in the gym, it probably means I'm also a bodybuilder, something like that. Yeah. So if I'm friends with people who program, I'm probably a programmer as well. So normally you'll mix with people that are close to your interests or similar in some way. So the links that you have or the links that this node has can actually tell you something about the node itself. Okay. This next thing is a protein molecule. This is actually made up of a few benzene rings and then some oxygen and hydrogen atoms. So again, you can see that there's some form of interconnection between the molecules. Okay, and this interconnection is node specific. Okay, like for example, if I would look at this node here, this node itself is linked to 3 different nodes here. Okay, and then this blue node is linked to 3 different nodes here. So it's node specific. It has a certain connection, and based on these linkages, it forms certain structures. So we can exploit the structural links or what the neighbors are linked to, and the neighbors, what other neighbors are these neighbors linked to, and so on. You can do some form of processing of data using the links. You will get more information about this molecule. Okay, so the last thing that I'm going to show you is like a GPS. Like for example, this is a node in your GPS. Okay, I use a different color. All right, and then if let's say I want to find like a shortest path from this node to this node, you can model your traffic as a graph. Okay, I mean y'all are programmers. Have you all heard of algorithms like Dijkstra, Floyd-Warshall, like graph first search, depth first search, that kind of graph algorithms? Yeah, so this kind of algorithms can be applied on a graph. So similarly, graph neural networks can do similar algorithms as well. Okay, if you use graph neural networks, you can approximate all these programming algorithms as well. So this enables like you to solve problems like shortest path as well using graph neural networks. And there's another thing that is not shown here is like relational networks. So for example, if you have like maybe you have house, okay, and then like house, and then you can put like house contains. Okay, this like it can be like relational where you have different nodes that link to each other with certain attributes, or it could be like causal. Yeah, so this kind of things, okay, relational graph or causal graph, okay, can all be modeled as a graph. Is it anything that can be modeled as a graph? You can potentially use a graph neural network to solve it. Okay, so one thing about all these things, if you notice, is if we were to use traditional neural networks, can you think of any neural network that can help to model this data well? Like, can a CNN do this kind of things well? Anyone? Do you think a convolutional neural network can do this kind of graph structure, like benzene rings, social networks? Do you think CNNs could model this? Okay, so that's what we'll find out. Okay, so I'll have actually a 5-minute video. This is actually a great resource. Okay, I would encourage you all to watch the full video. Okay, I'll be covering more in depth than what the video covers today. Okay, but I want to show you a short 5-minute segment here because I think it's quite interesting and the animation is really great.
Can I say something, Changmin?
Yes.
If you look at the adjacency matrix of the graph, that's almost like an image. So maybe CNN could do it like that.
Yes, but they don't really exploit the properties of the graph that well. I mean, if you treat it as an image for adjacency matrix, you still lose out some information. Yeah, but okay. And anyway, let me move on. Share sound. Okay, can you all see this? Okay, I'll just be playing this. So enjoy the 5-minute clip.
This web of data can actually be viewed as what we call a graph in computer science. But what is a graph exactly?
Okay, so before the video continues, this is about a social network, and in particular, the problem he's trying to solve is like some social matchmaking, like who is a potential better target for a certain like girl or guy. Yeah, so these are the attributes you see in the square here. Like when you go to like a dating website, your age, your gender, your occupation, and so on. And these are the links, like maybe your friends that you know each other from. Okay, so you can see that this is something that maybe Facebook would already have. All right, let's continue.
A graph is a structured way to represent data. It consists of nodes to represent entities like people, and edges to represent the relationships between these entities. Like in Andy's network, each node might also have a set of features which describe it. For edges, they could either be undirected, meaning two-way, or directed, one-way. Extending from undirected to directed graphs is not difficult once we get the basic mechanisms. So let's stick with undirected edges for now. But why graph neural networks? If you're watching this, I'm sure you've heard of the expansive success that neural networks have had on many problems. They are able to learn a variety of desired outputs from several types of inputs, such as numbers like stock prices, words that we use every day, or even images like this low resolution 4 over here. So why don't we just feed Andy's network through the all-powerful neural network and let it tell us his best match? Well, it turns out that neural networks have mostly been successful on more structured data types. For example, numbers belong in a series. Words that we use every day are found in sentences.
Like transformers.
And
yeah.
images, well, they actually come as a grid of pixels. But neural networks still struggled with more complex data such as graphs, which do not have any fixed structure or ordering. So, in order to reason with graphs, researchers went back to the drawing board to study what made neural networks so successful. The first layer in a common convolutional neural network takes each pixel and extracts information about its region by aggregating the pixel within the context of its neighborhood. The next layer then extracts information about that region within the context of its neighboring regions. Doing this over enough layers, the network will be able to reason over different parts of the whole image. And then with some linear computations, it can finally identify the relevant object.
So this is the structure of
Take
a
a second to
CNN.
think, how might you apply this mechanism to graphs? If we look closer at an image, we can actually view it as a special type of graph. A grid graph that is structured, and every node is a pixel that is connected to its 8 neighboring pixels. Seeing it like this, you might think to yourself, Why don't we just use the same aggregation mechanism that we have seen before? And you're right, we can actually use that same intuition on graphs. Relaxing the properties of fixed structure and ordering, we can similarly gain a better understanding of each node by aggregating the messages received from all neighboring nodes. Now, hold on to your new message, Andy, as your friends complete their first round of message passing. Observe how the color of each message changes to represent the newly aggregated message. And with each new round of message passing, more and more information gets passed around in the graph. Over sufficient rounds of message passing, we will eventually obtain a final representation of each node in the graph that will describe it given the larger context. Now we can actually also view the rounds of message passing as a series of layers, just like in our convolutional neural network. Here we go from the input to round 1 of message passing and then round 2 of message passing. And this produces our final understanding of nodes.
Okay, so I'll stop here and we'll go back to the slides. Okay, so that was actually quite a good animation about how the structure of your graph neural network actually is inspired by convolutional neural networks. Just that instead of having the pixels in a square, people are thinking, what if the connections are arbitrary, like you have different nodes and so on. There's no real structure we can have to represent it right now with current neural networks. And so people decided that why not I do my neural networks over the graph, using the graph connections as my connections to the neighboring nodes. So you can see that just now what was described is called message passing. It basically just means that there will be a sharing of information between nodes at each round. So you can think of it like if you were to do a telephone game where you need to pass the message from one point to another point, it's like in round 1, okay, you all played broken telephone before? You need to pass a message from first person to the last person, then the last person need to decipher it, right? So in round 1, the first person will pass to the adjacent neighbors, okay? And of course, in message passing, all of the nodes will actually pass to the neighbors some information. Okay, but all these people here don't really have anything. So in the game of telephone, only this thing is important. So round 1, you have that. Round 2, you will have this node pass to this one. And round 3, you have node pass to this one. Okay, so a quick question over here. So if this is round 1, round 2, round 3, okay, how many nodes do I have here? I have 4 nodes. So if let's say I have n nodes, how many rounds of this message passing do you think I would need in order to get my message to pass through from one node to any node in the graph? Anyone want to try? So for 4 nodes, I need to pass 3 times. Okay, for n nodes, how many times do I need to pass my message? Anyone want to try? Or maybe I just ask, maybe for 5 nodes, how many times do I need to pass the message in order to spread the message throughout the entire graph? Yep. So anyone want to try? Chicken, you want to try? Okay, there's some answers. Okay, n-1 rounds. Okay, that's correct. So if you have n nodes, you use n-1 rounds because that is the most amount of transition you would need in order to pass your message through the entire graph. Okay, so n nodes, you just need n-1 passes. So n-1 rounds. So you can treat a graph neural network something like a CNN, okay, like this is like 1 round of filters. And then from this information here, you apply the filter again to do some form of sharing of information. And it is very important that we share the information along the links that each node has, because that is the structure that we want to sort of utilize, okay? We use the links that each node has in order to determine who it can share its information to. So at each round, each of the node will get a little bit more information from the rest and so on. So eventually you will get some output, okay, which you can then pass through end to end in a typical neural network manner. Okay, so actually graph neural networks and traditional neural networks are actually the same, okay, in terms of what you want to do. Is only this part here uses the graph structure. Okay, so this part here is different, but at the last part, when you want to do like your classification task, is actually the same kind of method that you use for any other neural network we have learned before, like using cross entropy and so on. Okay, just that the way we do the sharing of information or the way we do the filters, if you look at it in a CNN context, will be different based on the connections of the graph. Okay. Question so far for this? Okay, I hope this is clear. Okay, I think the video is quite nice. You recommend you to watch the entire thing. 17 minutes is not a bad video. Okay, so let me give you an example of like how you can use a network in order to like maybe find the maximum value of the node in the graph. So at step one, okay, okay, this is actually not really step one. This is like initialization. Okay, this is the node values. And at each step, what I do is I will take the maximum value for my neighboring nodes, okay, and myself. So for example, like this node here, it takes in this node 9 and this node 4. And so what's the maximum value? The maximum value becomes 9. So it gets updated. And this node gets updated because this passed the message to it, and then it knows that. So basically what we have to do for each node is just take the max, okay, value of itself, okay, and also the neighbors nodes, neighbors. Okay, I hope this is clear. So each node itself, okay, will be updated, okay, to the maximum of itself and its neighbors nodes. Okay, so this is the algorithm that we are using to do this network. Okay, so for the next step, you can see that this node has been updated to the maximum value of 9 because this node has passed the information. And then lastly, you can see that over here, this node has been updated to the maximum value of 9 because of that. Okay, so if you were to just be interested in finding out what is the maximum node value, okay, you just need to run the network through n-1 times. In this case, it's 3 times. And then all the nodes will be the same value. Then you can just simply take the value of any node in the graph and you get the maximum node value for the entire graph. All right. Or rather for that section of the graph. Okay, so someone asked, I think it's Oyo, you asked, we need to decide which node to start. Actually, don't need to, because you realize that when you do this message passing, all the nodes actually pass the message at the same time.
Oh,
so there's,
I see.
Yeah, correct. There's no starting node. So like even this case, this 4 can be updated because everyone will just like pass the message. And then when you receive the message from your other nodes, then you're like, oh, who's higher? Is it myself or other nodes? Then you just choose the maximum value here. Okay.
Oh.
Yeah. Using a similar kind of algorithm, you can also do like shortest path. But shortest path, that one, you need to know what is the starting node. So if you want to do like shortest path, you need to like have the goal state as 0. And then the rest of the nodes as like -infinity. You know, it's something like the usual graph algorithms. Okay, then you just basically take the, actually not -infinity, it's +infinity. So you just like update the minimum in this case. So if you want to do like shortest path, you still need to have the age information as well. Okay, which I'm not going to cover today. Okay, you need to have the age information. Then you can like, for each iteration, you can update, okay, this one the cost is 3, then the cost here will be 5, then the cost here will be 9. Okay, so if you want to do like shortest path, you can also do a similar algorithm, but you need to define, okay, what is the starting node? You need to set it as 0 and the rest +infinity. So this is like the usual Dijkstra graph algorithm that we do. Or Floyd will show you. Basically, you can use this to do like graph problems. Okay, I'm just over here in this example, I'm giving you the simplest example possible that I can think of to just illustrate how the message is being passed through the entire graph. Okay, I hope this is clear how this works.
Yeah, thank you.
Okay, so now I'll go through a brief overview of this graph neural network. There will be a bit of math, okay, but I will just give you the concept more than the math. Okay, so this is what we saw in the video just now. We have the input. Okay, the input of a graph consists of like an adjacency matrix and a feature matrix. Okay, so what's an adjacency matrix? An adjacency matrix basically just means that if node 1 is connected to node 2, then that part of the matrix will be a 1. Okay, so I just draw a sample adjacency matrix here. Okay, so let's say this is node 0, 1, and 2. 0, 1, and 2. Okay, if node 0 each node is like connected to itself. So this will always be a diagonal matrix with 1. Let's say 0 is connected to 1. Okay, that means 1 is also connected to 0. Okay, so let's say we have a graph like that. Okay, so this graph will basically mean like this. Node 0 is connected to node 1. Okay, and node 2 is by itself. Okay, can you see that? So this adjacency matrix is a 1 if the two nodes are connected, and it's a 0 if they are not. Okay, so if you want to do like directed graphs, you can actually like change this to 0. So you saw in the video, they say that you can just do directed graphs. So like it's 0 to 1, right? So it means that this graph is a one-way. 0 goes to 1, but 1 is not linked to 0. Okay, so you can use this to specify a directed graph as well, just by changing the adjacency matrix. Okay, then what is this feature matrix over here? What is this X over here? Okay, so n is the number of nodes. So adjacency matrix, you know, if there's like 3 nodes, it's 3 by 3. Feature matrix is like n by f. F is the feature dimension. So what do you mean by the feature matrix? Okay, the feature matrix is something like, you know, just now in the social network, you have like age 25, male, doctor, male, and so on. So these attributes, okay, you can put them, you need to put them into numbers, of course, because neural networks use numbers. So 25 can still be 25. Male, female, I'll leave it as an exercise to you, or you can tell me male, female. If there's 2 classes, male, female, how do we make this a number? Anyone can give a guess? How do you represent a binary class as a number? Yeah, 1 and 0, correct. So you, based on the number of classes, you can do categorical encoding. See, all of you are good engineers already, you see? So easy. So you can do all this like that. And then you can represent all this as like a feature, as a feature vector. Okay, in this case, my f, the number of elements in this feature matrix, okay, is just 2, okay, because we have 2 features only, 25 and male. If you have a third feature, then this will be increased. Okay, then what you need to do is you then need to stack this up. Okay, you need to stack this up n times, okay, where n represents your number of nodes. So each node has a certain feature. You stack them up into a feature matrix X. Okay, so of course, if you were to do like this kind of graph neural networks, it's the same as like doing a multi-layer perceptron or CNN. It's best to actually, you should actually normalize your features as far as possible. This will help the gradient become like more uniform, and then you can converge better. So you also should do some form of feature normalization. Okay, some packages like sklearn can do that for you automatically. So once you get this feature matrix, this will be this X over here. Okay, so a graph consists of these features plus the adjacency matrix to define the connections. Okay, there's also, if you want to talk about like more complicated graphs, you also have edge embeddings as well. Okay, where basically like each edge embeddings, okay, will be basically the feature space on the edge itself. So it's like number of edges times the feature. So edge embeddings are only needed, okay, if, okay, there's some information that we want. If there's some information that we want to store in the edges, like, you know, in the shortest path algorithm, you want to store the distance in your edges. Okay, but because this is like an extension of the graph neural network concept, okay, today we'll just keep things simple. We will not talk about edge embeddings. Okay, I'm just giving you here because I'm just letting you know that there's such a thing as edge embeddings. It's a similar concept to the feature matrix. Okay, it's just applied to the edges. Okay, the information stored in the edges rather than the nodes. Okay, so there's this
is different, right? This F is not the same as this F, right?
It depends on whether they share the similar feature space, the nodes and the edges.
It could be different, right?
It could be different, yes.
Okay.
Yeah. So I'm just giving you this over here for completeness. Okay, but do be aware that for today, for simplicity, I will just leave out everything regarding edge embeddings. Okay, because it's actually quite complicated if you include that as well. Okay, so now that we got the input settled, okay, then what do we do now in order to pass the message? Remember, we want to send our envelope to the neighboring nodes, and you want to repeat that for many time frames. So the first message passing layer is this hidden layer here. We basically, each node, okay, will take in the message from all its connections. Okay, and how do we know what are the connections? We use the adjacency matrix. Okay, and then similarly for this node, it takes in the message from all the surrounding nodes here. Okay, so this is the way to do message passing. Okay, and then we basically aggregate the information, either take like the maximum, minimum, average it, or you could apply some function. Okay, so this is the beauty of neural networks. Okay, you can actually apply a function f, okay, that transforms like itself, okay, and its neighbors. Yeah, so there's a function here that it can transform itself and its neighbors. Okay, maybe I should type it out. Okay, it looks nicer that way. Yeah, so you could have a function that is learnable, that transforms itself and its neighbors, and then you can map this, okay, to this. Okay, so actually this is actually known as H in the literature. H as in the hidden layer. Okay, it's like, you know, when you do MLP, you have a hidden layer. So whenever you do this message passing, you aggregate the information. This node here, okay, instead of referring it to as X, which is the input, okay, so all these nodes here are referred to X. These intermediate nodes here are referred to as H. Okay, but it's probably going to be the same. It can be of a different dimensionality as your original input. You can compress it and the hidden layer. So similarly, you can do another round of message passing using this, like H1, you can get H2, okay, the second hidden layer of your graph, okay, which is the next round of message passing. Okay, and finally, after you finish, okay, your final output here is actually all your H2, okay, because this is the output space after we pass the message twice, right? So that we can apply some functions here, like maybe G, okay, to this graph. Okay, depending on what we want to get from this graph, we apply the function here. Okay, I will tell you some of the common functions that we apply to the output of graph neural networks later. Okay, so the main idea is that we pass messages between the nodes and we update the nodes information at each time step. And we can keep repeating that for as many layers as you want. Okay.
So Changmin, you showed a ReLU between the layers. Did you talk
yes.
about that again?
That's meant for like non-linearity. You can use any other things as well. You can use sigmoid, you can use 10H.
But you have a vector. So how are you going to apply ReLU to the vector? Is it element-wise?
Yeah, element-wise.
Okay.
Yeah, so actually you may not need this ReLU here if you have a form of non-linearity here as well in this F. Okay, because you all know if you don't apply non-linearity, no matter how many layers you add, it will still be as though as it's a linear network. Okay, so the non-linearity is important here. So your non-linearity, you can also apply it in the F itself. Like if you were to do something like a max or min function over here, that can be your non-linearity as well. Okay. Just to let you know, this hidden layer, the way you process it in the first hidden layer and the second hidden layer may be different. Okay, so it's like a CNN. Your first level filters and your second level filters might be different filters, right, in the CNN. Okay, over here, we actually don't really share weights between the first layer and the second layer, although technically you could as well. Okay, so actually they can learn different relations for the first and second layer and the third layer and so on. Okay, there's really a lot of possibilities for graph neural networks. I mean, some people try this, some people try that. It's still quite an open topic for research. In fact, as I was reading up to do this slides, there's like so many variants, I think up to 100 different variants of graph neural networks. Okay, but the ideas are very similar. The idea is to use the connection information between the nodes in order to do some form of processing. Okay, how you process, that one is for people to get their PhD. So they do variant 1 is PhD number 1, variant 2, PhD number 2, and so on. Yeah. So we just need to know what is the most important thing. The variants, I don't think it's that important. Okay, you just need to know that you traverse the graph using the information available by the connections. Okay, so this is the first slide I want to go through. So this is the traditional convolutional neural network. You can see that this is the filter, and the filter basically you can treat it as like 8 different nodes. Okay, 8 different nodes plus a center node. So typically in a filter, what you will do is you probably will sum up the entire feature. Okay, so these features usually Okay, after you sum them up, you will apply a ReLU in order to see whether you have that feature or not. Okay, so this is like a traditional filter. You just sum up the inputs with respective weights, and these weights are like your filter weights. Like for example, if your filter is like, okay, let's say our filter is like 1 0 0 1 1 0 0 0 0. So like some filter like this might be responsible for just like finding out which are the horizontal lines. A filter like this. So this one is actually in this weight over here. So you can see that in a traditional neural network, it can be viewed as like a graph as well. Okay, rather than viewing it as a square, you can view it as a graph where the middle node connects to all the adjacent nodes. Okay, and then you then do message passing. Can you see a message passing here? All the surrounding nodes actually pass a message here. It's just that you add up all the messages for CNN. Okay, and you also add up the middle node, of course. Yeah. So it looks like this. So you add up total of 9 nodes. Okay, and then after you apply a form of non-linearity. Okay, in this case, the non-linearity is denoted by this sigmoid sign here. Okay, but you can also use ReLU. Okay, remember CNN, we use ReLU as activation. You can also use ReLU here. So the update for the filter itself is basically after you sum up all the weights, okay, then you update the hidden state, and then you repeat that for all the nodes, like for this node here, for this node, for this node, for this node. So you can see that we actually perform message passing for every single individual node of your CNN. Can you see that? Okay, so when we do like, remember last time we talked about the sliding window of the CNN, okay, the strides and everything, actually is similar to message passing. All the nodes pass to each other. Okay, and then like we sort of ignore the edge nodes here because like the edge nodes here don't have like, the edge nodes here don't have extra connection, so we ignore them. Okay, but you can also choose to zero pad it, then you can do the message passing for the edge nodes as well. Okay, if you all understand what I mean. So like, because typically depends on what kind of like, is it same padding? If it's same padding, then they will do like zero padding. Yeah, if it's like valid padding, then it will be like a shrinking, that you don't care about the edge nodes. So you can view this as one round of message passing. So can you all see this? Okay, so this is how a CNN is. No difference from a normal CNN. I'm just showing you how to view a CNN as a graph. Okay, can you all see how this can be viewed as a graph? All right, all clear so far? All clear how CNN can be viewed as a graph? Okay, because now we will be going through the next part, which is the graph convolutional network. Okay, so graph convolutional neural network and this one over here actually is the same thing. Okay, just that in this case we relax the restriction. Okay, we say that okay, we don't really need it to be in the form of a square anymore. We can like use any arbitrary connection over here. And what we do is actually the same thing. We sum up the weights of the current node itself. This is node 0. And then for all the neighbors here, this Ni is the neighbor indices. For all the neighbor indices, I sum up the weights as well. Okay. But over here, there's a slight difference. Okay. Over here, we also have a norm constant here. Okay, to normalize it. Okay. In a CNN, okay, this is actually 1. Okay. In a CNN, this is 1. Okay, because we sum up all the weights evenly. Okay, but when we want to do message passing, typically we want to weigh this like by the number of nodes, number of neighbors. Okay, because if we want to preserve this information here, okay, we want this information here to be like of a comparable magnitude to the messages received. Okay, because if not, you can get easily overwhelmed. This part here can easily overwhelm your original information, and then you might lose out. This is your original message, original information in the node. So you don't want to. You actually don't really want to lose out everything. Okay, here, so we normally normalize this, or we weigh it such that the overall magnitude of this is equivalent to the original information, or it can be even smaller. So this one can be learnable or can be fixed. Okay, typically what people use is the number of nodes. So if let's say there's 4 connections here, this Cij will be 4. So you weigh each node by 1/4. So you average it out. Okay, some people also include, okay, the neighbors as the node itself. Okay, this is possible because a node can connect to itself as well. So it can be its own neighbor as well. So this is the original information in the node. And in fact, the node itself can also be included in this right-hand side as well. You can average the message over 5 different connections. Okay, so it really depends on how you define this. So if it's a self connection is counted as well, you can average this part over 5 nodes or over like itself plus the neighboring nodes. Okay, so you can see that over here, okay, we just need to tweak this Cij parameter here. If the Cij parameter is 1, this is the same as a CNN in terms of the update. Okay, but because if you want to weigh it differently, then it'll become a graph convolutional network. Okay, is this clear so far for this?
It's
Okay,
odd
so,
because there already are weights, right? Your WI are also learnable.
yes. The
It's very
W
odd
are
that-
learnable.
So there's like 2 sets of weights. Your Cij are some weights you learn, and the Wi are like weights you learn. It seems very odd.
Yeah, typically you can actually subsume your Cij into the weights here.
Yeah, that's what I would think.
Yeah, you can actually
Because whatever you said about not overriding the information the node has, why doesn't that happen in CNNs?
because in CNNs, what we want is we want the overall sum of all the messages. So we don't need to average out.
No, I mean, why? I mean, why isn't the idea of overriding what's at that pixel, right? Why doesn't that same argument hold for CNNs? So
Because CNNs, what we want to do is we want to find out a particular structure. So like you want to find out a horizontal line. So you don't want to like override or what. We just want to find out like whether this band is there, then we activate based on that. So the idea of overriding is not really very strong here. We actually want to treat each pixel equally because we want to view in that 3x3 patch what kind of pattern are we finding.
but in the example you gave, you chose the filter, but typically the filter weights are learned.
Yes.
Right? I mean, you set a filter and said I could use it to detect a horizontal line, but in the typical use case of a CNN, you learn the filter weights. It's the same exact problem as the next page. So whatever you set on the next page, I feel like should hold here. So it's like those CIJs are, in my opinion, very fishy. But anyway, it's okay.
Yeah, I mean, it really depends on. So even if you do the wrong Cij, it's fine also because your weights can compensate for it.
Yeah, that's what I thought. Right. Yeah.
Okay, shall we move on? Okay, so now we talk about the last structure I'm going to share. Actually, there's another one called message passing, but I will not be covering that today. I'll just cover another popular architecture called the graph attentional network. So the graph attentional network, okay, this is very, very complicated. Okay, I don't need you to fully understand what is this, but let me give you the intuition behind it. Okay, so suppose you have a node H1, okay, and this, oops, I use a purple color. So let's use a red color. So let's say you have this node H1, and then you have information from the various nodes, right? Like all these nodes pass you the information, right? Okay, what if, Animal Farm, right? All nodes are equal, but some nodes are more equal than others, yeah? So some nodes actually carry more information than the other nodes, right? So okay, even yourself, you also can do like that. So what if I told you that you need to sort of attend to each node differently. Based on the importance of each node to your task, you attend to it differently. So you give it different weights such that total sum of these weights sum up to 1. So you can see that, okay, this number 1 here, this weight number 2 here, okay, this number 3, number 4. Okay, I'm just going to draw like all the arrows as one number. So your summation of 1, 2, 3, 4, 5, 6. Okay, the summation of all this, okay. So the attentional indices add up to 1. Okay, so it means that I have to spread my attention. I have a limited amount of attention. I will spread my attention to the different people around me or the different connections around me. So it is a form of like imbalanced way of updating. I don't treat each node equally. I let the attention in this tell me, attention index tell me how much to focus on for each node. So if that node is more important to me, I focus more on that. Okay, how do I know what is more important? It depends on the loss function. Okay, so you can learn this attentional index Okay, and this is actually given by a softmax. Okay, this whole very big equation here is none other than softmax. Okay, it's none other than softmax of basically a concatenated like weight matrix times the node itself. So this is basically a way to do attention over like two nodes. So like given two nodes f, h1 and h2, okay, you get a form of you get a value, and then you take all these values, okay, all these values from each pair of nodes, okay, and then you just do a softmax over all these values. You will get this equation down here. Okay, so you will get this thing here. Okay, so this looks very complicated, but actually all it does is that you train a learnable function f, okay, that maps in two states together, h1 and h2 or h1 and h3. Okay, over here they did a concatenation. Okay, so it doesn't matter really how you train this. Okay, as long as you take a function that involves the starting node and the neighboring nodes, you take a function that tells you how important this connection is, you get a certain value. Okay, of course we also do the same value for like h1 and h3 and so on. Yeah, you do for all of them dot 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 until f like h1 to h6. Okay, over here we also have h1, okay, because like h1 connected to itself. So I'm just going to put this here for completeness. Okay, so you do all these things here and then you do a softmax, you get this attention in this here. So the benefit of doing softmax is that, you know, when you do a softmax, all these values you add up together, okay, will be equals to 1, okay, because you see, you can see why this add up to 1, right? Because if you were to look at the bottom term here, this just sums over all the nodes. So by the very fact of softmax, you apply softmax over all these values, you will get this. You will get all the attentional indices sum up to 1. Can you all see that from the equation itself? Because of the base here, I just divide by all these values here. I divide by that. So that's why if I sum up the softmax values of all this, you add up to 1. Okay, so this is my attention in this that I put here. Okay, and then over here, this weight and the hj is exactly the same as what we saw previously. We just add up, okay, the weight matrix by itself times the node itself. So over here, we don't have a special term for the self update. Okay, this is also represented by this weight over here. So whatever problem who said just now, yes, okay, it need not be treated separately. In the graph attentional network framework, they treat the self node as the neighbor as well. Okay, so there's no distinguishing function for the self value. It will all be put into this attentional framework, and then we will just see what is more important to take note to bring to the next step. Okay, so you might be asking me, what is this K over here, right? Okay, so this architecture is actually quite complicated. Okay, I'll be showing you the code that implements this later. So this K is actually multi-headed attention. Remember transformers? Remember transformers? Yes, so now we don't only have just one attention framework. What if we have like many attentional frameworks? So imagine we have attention head 1, attention head 2. Each of them have different attention weights. Okay. And then we have K of them. Okay, and what we do next is we take in these outputs from these attentional heads and then we do an averaging. Okay, and that's exactly what this formula here is showing you. Okay, and all this K over here, this is not to the power of K. This just means the weight indices for attentional head K and the attentional index for attention head K. So if you take away the K here and you just do like a single layer of one head of attention, okay, this formula, okay, without, and then you set this thing to be like 1 or set this thing to be C, okay, Cij, which is like similar to what we saw in the earlier slide. If you set this to be 1 divided by Cij, okay, let's go back to the slide. I want to show you this. Okay, it's actually the same equation as this. Yeah, of course, we also need to put a Cij here, but you can see that if we were to ignore the multi-head and then we replace the attention with like a fixed value, Cij, you can see that you will get back a graph convolutional network. Can you see that? Okay, so this is the thing about GNNs, okay? So actually this GCN can be expressed totally in a graph attentional network. Okay, just a quick trivia. You all know why graph attentional networks is GAT and not GAN? Anyone want to guess why? Chicken, you might know the answer. Why do you think they didn't call it GAN?
Is it because there's already a GAN?
Yeah.
Yes, correct. So GANs unfortunately came first before this graph attentional network, you see. So they bopian. So they have to just, instead of taking the word, they have to just do like that, GAT. Yeah, so in machine learning or in like a lot of stuff, when we invent, first mover advantage, if you are the first person, you get to pick the name. If not, you just have to make do with whatever's that's remaining. Okay, so this is a graph attention network. And based on the logic that I described just now, you can see that GCN, okay, can actually be expressed more generally as a graph attentional network. Okay, and actually there's also another form of network called message passing, okay, which basically is a way to do like, so it's a more generic form of this. Okay, you need not only be restrained to like nodes like that. You can actually have an intermediate representation, and then you can update based on an intermediate representation. Okay, so if you're interested, go and search for message passing. Okay, I will not be covering that today. Okay, so today I just need you all to understand that a GCN is very similar to a CNN. Okay, it's just that we do an arbitrary graph structure. Okay, and a GAT just basically adds an attentional component, okay, when we do the message passing updates for each node. Okay, so a GAT is a more generic version of a GCN, and a GCN is a more generic version of a CNN. So you can see all these are linked actually. So the more we go in graph neural networks, the more generic our structure is, and like the more like flexibility we can endow in it. Okay, so one thing for GNNs right now is that each node, the update formula is the same regardless of whatever node there is. Okay, there's some work that tries to break this norm to make like the update different for each node. So yeah, there are some existing works going on. I think that's the way forward actually. We are trying to make our network more and more generic, okay, that can be more flexible to apply to different situations. So this is still a very hot area of research. I expect more papers to be published on this next 2 to 3 years. So whatever I say now might be might be outdated next year. Yeah, so that's how fast the field is moving. Okay, so this is just the preliminary, okay, for you all to understand what's going on. So
I have a question, just to pause here. So one hidden layer, let's say you have a generic function that sums up 6 of the neighboring nodes and with a weight. What if that node does, or some nodes don't have 6 neighbors? What if they have, some nodes have 2 neighbors and another node has 100? How does that work then?
Then in that case, based on this connections here, you will have fewer terms to sum up. So you will still be able to, but then the thing is when you do like GAT, you will still attend to all the neighbors, and all this attention must sum up to 1. It's just that in some nodes you attend to only 2, in some nodes you attend to like 100. And in this case, all these weights here actually will include the maximum number of nodes. It's just that for those nodes that are not connected, then these weights will be ignored. Yeah, so in terms of the attention, the way we attend for each node is the same actually. It's just that based on whatever neighbors that are present, okay, your this weight thing, you might actually omit some rows of this weight matrix. Yeah. Yes, Prof. Mehu, yep, you got a question?
Yeah, I was just curious. Why do you use softmax here to?
Oh, because you want to sum up to 1.
No. Let me finish. I said, why do you use it to normalize? There are many other more obvious ways of normalizing. Why do we use softmax?
What other ways do you recommend to normalize?
I mean, the simplest way is just divide by the max, just divide by the sum.
Yes, okay. You can do that as well. I would say that softmax is better in the sense that it allows for perhaps some form of lateral inhibition, because when you do an exponential thing, the larger value tends to dominate. Yeah, so it might be the case that some form of lateral inhibition might actually help the network learn better.
Okay.
Yeah, compared to like not having any like softmax, like averaging.
Okay, thanks.
But that's an interesting point actually. Yeah, that's an interesting point. Okay, so how do we do the network itself? So you can see that, okay, it can be very concisely represented as like, okay, this is your original X itself, okay? It can be represented as H0. And then for each layer, what we do is we take the previous layer H, okay, multiplied by some form of weights, okay, multiplied by maybe your adjacency matrix. Okay, this is actually a shorthand to like do the whatever you saw earlier where we take the neighboring nodes. Okay, so you just multiply by adjacency matrix. You can do this everything in matrix multiplication. Okay, but just to let you know that now this adjacency matrix in the code that I'm going to show you, actually we don't really have this A. Okay, we actually do like we actually find out what are the neighbors and we add them up ourselves. Okay, we don't really use this A in the code, but you can make it more efficient by putting this A inside here. Right? But if you want to do more complicated functions like message passing, okay, you can't really use a matrix multiplication because you have to do two steps. You have to form a message, and then from the message you update the nodes. So yeah, this is just the for like GCNs or GAT, you can do this kind of formula. Okay, so this is the generic formula to update the nodes in each round of like message passing, a very simple message passing. Okay, and then at the end of it, you have your final hidden layer HN, and then that's when you can do your different stuff to it. So if you want to do like node classification, like you want to find out whether this person is a male or female or something like that, you can then take a softmax over all possible classes. Okay, and then you can do like cross entropy to train this as your like, it's a typical classification problem. Okay, so yeah, you can do that. So later we will be doing that for our Jupyter Notebook. We can also do like graph classification where we just sum up all the hidden states in the graph, and then maybe we like do a softmax over this, the entire sum. Okay, in order to find out like maybe is this graph, you can just check whether like maybe the graph is the graph fully connected, or is the graph split into 3 parts. There's different ways to classify graphs. So you can add up all like the hidden node states, and you can then classify your graph accordingly. Okay, the last part is link prediction. Link prediction is maybe something like, are these two people friends? Okay, so what you do is you take in like maybe the hidden state for the two of them, and then you just like do some function, okay, and then you output like the probability of them being friends. Yeah, so this is link prediction. Questions so far for this? So these are just some uses. After you pass the message through each node, you need to find out like an objective that you want to do. The objective can be per node for the whole graph, or it can be in a link between two nodes of a graph. Okay, so as I said earlier in the first slide, you can treat this part here. Okay, this part is like processing over a graph. You can treat this part maybe like a CNN. Okay, or in this case, this is a GNN. Okay, this part here is really just to process information in the form of a graph. And then this last part here is the typical classification process that we normally do for like CNNs. Yeah, so you choose whatever aspects of the information we want to capture, and then that will be our part that we classify here. Okay, if nothing else, I will continue. I have to review later. You want to ask anything now? Okay, so I just want to share with you. Oh, sorry. Please go ahead.
No. Thank you.
Yeah, no, so GNNs, don't worry. GNNs are very complicated. Okay, this is, if you can understand this, you are like maybe the 1% in the world that know this, because actually this is very new. This is like fresh out of the oven kind of stuff. Okay, so in fact, it was hard for me to do this set of slides as well. Okay, because this is something quite new as well for me. Okay, but okay, now we move on to this part. I just want to share with you something. Oh, hang on, let me just. Okay, so I just want to share with you all something of the properties of a GNN. So there's this property called permutation invariance. And this permutation invariance here is something that actually helps you to generalize better. What do I mean by permutation invariance? Okay, so these slides I took from some geometric deep learning slides by Peter Velikovic and company. Yeah, so this is a very nice set of slides, I feel. We have like an adjacency matrix here. Just now I told you all like this is the start node and this is the end node, and black means it's connected. So in this case, 1 is connected to 2, 6, 4, 10. Yeah, so you can see this one here is connected to node 1 is connected to 2, 4, 6, 8, 10. Can you see that? Okay, and then this has a feature matrix of size D. Okay, in this case, D is 4. Okay, so one good property about graphs is that, you know, if let's say your graph, I were to jumble up the node numbers, but I still have the same connections here. Okay, if let's say I change this number to like 2 or something, but all these links are still the same. Okay, it doesn't make sense to process them differently, right? Because technically it's still the same connection, right? I just need to, if I reorder my numbers of the nodes here, okay, but the graph connection is still the same. Isn't it the same graph? It's still the same graph, right? Just a different numbering, right? So that's the beauty of graph neural networks. Actually, if I were to switch this thing here, I were to switch the node orderings here, okay, you will see that actually all I need to do is to just apply a permutation matrix to my adjacency matrix and a permutation matrix to my feature matrix, and everything can be processed the same way. Okay, and this is the property called permutation invariance in a graph neural network. It's very, very important. Okay, because with this permutation invariance property, you can actually evaluate graphs like very similarly. Basically similar graphs with the graph with the same connection, but like the connection can be like at a different part of the graph. It can be viewed similarly. You can generalize to other graphs more easily. Okay, the structure of the graph can be like sort of preserved and then used to analyze another set of graph. Okay, and if let's say I add in another node here, I add in node 13. Okay, because you can treat node 13 as maybe node 1 or node 2, right? If I were to change node 13 to node 1, I actually process it the same way, right? And I change this to node 13. My way of doing the graph neural network, the message passing will still be the same, right? Because it is order invariant, permutation invariant. I can just add in a new node 13, and then whatever I learned in the message passing for my earlier nodes here, whatever I learned here, like how to take the, like for example, in the first example I gave you is like how to take the maximum value of the node, right? In this case, I just need to take the maximum value here. That's the only operation I need to know, max. Okay, if I were to already learn that each node needs to do the max, I add in a node 13 here, I can easily use the same learn function because the functions are all shared between all the nodes. So I just plug and play a new node here. I can easily apply whatever I learned in the smaller graph to a larger graph. Can you see that? Because the way that you do the aggregation, the message passing is the same per node. It doesn't matter where I add the node in the graph. So I can add in 100 more nodes. I can add in 1,000,000 more nodes. And whatever you learn from maybe this graph of 11 nodes, okay, it can actually scale up and apply to the larger graph. Okay, can you all see that? Can you all see that a graph neural network, you can scale up easily because what we are learning in a graph neural network, we are just learning the function of each node. And this function of the node is the same regardless of position. Of course, when we do like more advanced research, maybe you want to vary based on position. But if the function of the node is the same per position, then it doesn't matter where your node is in the graph. Okay, so this property of permutation invariance and the way that you process the node message passing is the same regardless of which node you consider in the graph. This helps it to generalize quite well. Okay, I hope this is still okay for you. Okay, just take a quick survey. Anyone here is lost? All okay? Koyon, are you okay? Nakata, Ken? All right. So let me just move on to the next few slides. I maybe need about 15 minutes. Okay, if you don't mind, I might drag a bit. Okay, but I think let's finish this. Okay, so I just want to link this last part now to transformers. So transformers is actually a form of attentional GNN.
Sorry, can I ask you a question?
Yes.
Yeah, on the previous slide. So if you're doing the max function like you spoke about before, and you add a new node that's the max, then doesn't that information still have to propagate throughout the whole network?
Yes, so when you add the node, you don't add it in the middle of your processing. I'm talking about you add it at the start.
Oh, yeah, okay. I mean, if you add it at the start, then you're just having a new network, right? You still
It's just a new network, but you can apply what you learned in the smaller network to like a new, bigger network.
What do you mean by apply what you learned?
So whatever that you learned to do the message passing, how you process the message from each node, you can actually apply it to a larger network.
Are you talking about all the weights and everything?
Say again?
Are you talking about the weights and everything?
Yes, the weights.
So yeah, so this is like afterwards, right? It's like so I'm a little bit confused. So you still have to have like another whole layer though, right? Like you still have to do everything that you did in the layer.
Yes, as in you need to do the message passing for the new graph, but you can use what you learned before for the previous graph.
I mean, but that's just initial conditions. It's just an initialization.
Yeah, you can treat it as a different initial conditions, but the network is like already learned like how to process the graph.
Okay, thanks.
Yeah, okay, so let's continue. Okay, so I just want to link this last part to transformers. So for transformers, okay, you can treat it as a form of attentional GNNs, okay? So the link between each element is dependent on the element itself, because like it depends on like the key value, the query key attention over here. So this attention actually is quite different from the attention that we see in the GAT, okay, because there's no query and key, okay, for GAT is just a matrix multiplication of attention weights, but in this transformers is like there's a query and there's a key. But you can see that actually the way that we let transformers choose like how much to focus on each key, it can be viewed, okay, it can be viewed as a form of GNN, okay. So it's actually exactly the same as a GAT. A transformer is a GAT, okay, because it is completely connected, okay. So GAT that has a complete edge set means like all nodes connected to all nodes. When you do that, you get transformers, okay, and then we let each of the nodes choose what to focus on from the previous layer. Okay, and how do we add in the sequence information in transformers? They actually add it in through embeddings, like the sequence embeddings, positional embeddings that that happen at the start. Okay, because you know if you look at what we saw earlier in the over here, you see that actually there's no sequence, right? Because you can swap your nodes and the way you process the graph is the same, right? So in order to add some form of sequence to transformers, okay, this is in the sequence embeddings or positional embeddings. Okay, so that's more or less for the presentation. Now we will go through the practical. So we'll use a graph attention network on the Cora dataset. So actually, I also implemented a graph convolutional network as well, because as what I said, a graph attention network is a more generic form of a convolutional network. If we fix the attention weights, that's a graph convolutional network. So what is a Cora dataset? It is a dataset of publications, 2708 scientific publications grouped into 7 classes. Okay, and these 7 classes are like the topic, like probability theory, and some other topics. Okay, so your aim is to group each of these papers into 7 different distinct topics. Okay, there are total of 5429 citations. So like paper 1 will cite paper 2, paper 1 will cite paper 3. So it is in the hopes that like based on the citation links, you can see what papers are more linked to each other, right? Because if you treat like papers as like people normally cite similar papers. So if let's say I'm in probability theory, I tend to cite probability theory papers. So based on this link, you might get more details about what this paper is. Okay, and also we have the features of each publication. In this case, our X, the feature vector, is a 1 hot vector or 0, 1 vector to indicate a presence of a particular word. So like for example, the presence of the word probability, okay, presence of the word dynamic, presence of the word network. This might indicate what categories there are, okay, in the paper. So this is the rough scope of the problem. And then now let us see, okay, let us see how this works. Okay, let me go back to my, okay, where is it? Yeah, okay, let's go back here. Okay, so over here, actually, I don't think I have time to go through like in depth for this. Okay, but the main thing here, let me just change my runtime here to like GPUs. Okay, so just feel free to explore this notebook. I actually took this from TensorFlow website. It's called GAT for node classification. Okay, but I added in some GCN code, added in some self-links, some diagrams, and so on. So let me just roughly go through the code, okay? So, all right, so we let it run. All right, so the code basically is trying to classify the Cora dataset, as I mentioned earlier. So this is how a GAT looks like. Okay, a node is updated by its neighbors with some attentional weights. We import some packages. Okay, this is the processing of the data set. Okay, I won't be going through this. So we have a set of citation links from paper 0 to paper 21. So there's a total of 2708 papers labeled from 0 to 2707. And each paper has a total of 1433 terms, okay, of 0 or 1, indicating like 1 if there's a term there. And this subject is like the subject class. Okay, this is the list of citation, and this is the... So I can also, I did some processing. I plot, okay, the number of citations that each people have, and then like most of them have 0 like citations. Most of them don't cite anything, but then like, sorry, most of them don't get cited at all. But then there's like an exponentially decaying number of people that get cited. Some cited 40 times, but very little. So actually, this is very typical of papers. Okay, the more influential papers get cited a lot. Again, majority of the papers don't get cited at all. So this is like quite a skewed data set in some sense, because the links are quite biased to certain papers.
It's
Okay,
power
so
law.
sorry.
It's power law.
Yeah, correct. So this is typical of publishing, right?
Yeah.
Yeah, so this is the data set we are dealing with. So actually all these papers that we see over here, like 30 or 40 citations to it, can be quite easy to classify, because you can then use the whatever you know about all these 30 to 40 papers in order to find out the category. But all these like 0 here might be quite hard to classify. You can see that this is about half the data set have 0 citations. So we want to see like whether or not using the citation link itself, can we help to classify the things better? So, okay, this is how we split the data into train and test, half-half randomly. Okay, prepare the graph data. So I will not be covering this because this is not that important. Okay, this is the node states, which is like 2708 by 1433. So what is the model itself? Okay, this is the multi-header attention, similar to a transformer, but they don't use this dot product here. They actually multiply by an attentional matrix.
Sorry,
So
what's the input for the model? What's the input?
the input for the model?
Yeah.
Okay, so the model, when you construct the time, it takes in these ages and this node states as a given when it constructs the graph. And then once you actually train the model, you give it the indices of whatever you are training. And so the input to the model is like this. The input to the model. Okay, so when you actually train the GNN, your ages and the features are already all inside here. As in, it's already all, the model has all this information. The age list, and the feature list is all in the model itself. But when you train that time, what you give it here, you are giving it the index of the paper. And then what you need to output here is the class of the paper. So basically the input is just an index of the paper, like 0 to 2707. Yeah, so half of these indices are training and half of it are testing. And then you have to predict what class the paper is, which is like a class from 0 to 6. Yeah, 7 classes.
So the feature list and the age list are sort of like the model doesn't start with a random array of numbers. It is given the age list and the feature list as the starting point.
Yes. So it's quite different from like batch training, because you don't actually do batch training on the age and feature list. You only do batch training on the index. Yeah, so it is a little different from a traditional network, because there are
This is
some
the
things...
data, right? I mean, the edge list and the feature list. This is the data set.
Yes, but you don't use it for the training. These are actually all given to this graph.
Yeah, that's what I'm saying. You wouldn't have the graph without it. This is the graph.
Yes, correct.
That's what I'm saying. This is the data. It's the graph.
Correct. Yeah. So
right.
Actually,
sorry, but the data is give in a different matrix size. So that one is 5,000 plus times 2. Then the bottom one is 2,000 times 1,400, right?
What's the features here? It's the number of citations, right?
yes. The feature is a 1433 01 vector of whether or not it contains a word. So there are 1433 keywords that are used, and then they just basically 0 means the word is not present in the paper.
Okay, so that's the feature list, right?
Yes.
And the edge list is derived from the graph, right?
Yes. Yeah, so sorry, the edge list is derived from the citations.
Yeah.
Yeah. Is that clear? Can I move on?
Okay, we'll see how the model gets updated then. Like,
Yeah, sure. So this is how you build the model. Okay, so actually it's quite complicated, but I just focus
What are
more
the six,
on.
what are the 6 classes?
Oh, it's at the bottom. These are the classes: case-based, genetic, algo, neural networks, probabilistic, method, reinforcement learning, rule learning, and theory.
So it's trying to classify based on what words are in the paper title, as well as what the citations are.
Yes, not just the paper title. I think it's the entire paper.
Oh, the entire paper and also the what paper cited.
Yes.
Oh, okay, thanks.
So there are some things that I would like to actually invite you all to just look through. So like there are some things that I use in the code. Okay, like gather, where basically let's gather the original indices. Okay, but I don't think I have time to like really explain in detail what all this does. Okay, so I will just leave it to you here to explore. I actually wrote some comments here. So yeah, these are some stuff that they actually use in order to do the code. Okay, so the main thing, okay, this is the graph attention layer. This is the main layer. Okay, the main thing is we have two things. One is the weight matrix. Remember, we have a weight matrix W. So we initialize a W here. Okay, this is the hidden layer dimension, and then this is like 100 is, sorry, the hidden layer dimension, and 800 is the like original size. So this is like my H dimension is 100. So this is the weight matrix, and then we have an attentional matrix, which is the alpha itself. So remember the attentional matrix, we need to take in two functions, H1 and H2, right? We need to give like a value between any two nodes, right? So how they did it was basically they concatenate these two nodes together. Okay, and then when you concatenate these two nodes, because the feature size is 100, right? So the hidden feature size for these two in concatenation is 200. Okay, and then we can learn like a form of, we call it a kernel attention, but there's actually a matrix in order to extract out a value. So remember when we did all these values here, what do we do with all these values? Like V1, V2, we actually apply a, if you remember what we did earlier, we actually did a softmax in order to get the attention weights. So this kernel attention is just to convert the two hidden states concatenated together to a certain value. And then after that, we will softmax this value. Okay. So let's continue down with the code. Okay, so yeah, you can just look at this. Okay. The main thing is like, first we transform the nodes into a hidden dimension of 100. Okay. So 800 was the original dimension. Actually, the original dimension is 1433, but there's some pre-processing code in the next few lines, okay, that will convert it to 800 first. So the next thing will convert to 100. Okay, so we have this, okay, to have this, to basically have the hidden representation as 100. Okay, then we next do the pairwise attention score. First, we reshape it to be 5429, 200. 5429, you all know where this number came from? 5429 is the number of ages. Okay, so after that, we basically put our kernel attention in order to get you 5429 different values. Okay, remember? Then after that, what we need to do is we need to get the attention score. So what we do is we do a exponential with this, and we click the exponential index between -2 and 2 to prevent like gradient overflow, underflow. Okay. After that, okay, this part here is actually quite a cool thing. Okay, what they did is basically they just sum up, okay, based on the target nodes, okay, you sum up what are the, so you have your target node here, okay, based on all the ages information, because you have the age matrix, right? So you have all your source nodes that like, the source node will cite the target paper, right? So your source nodes will actually go cite the target paper like that. So what you can do is that based on your target node, let's say your paper is 0, you can label all these ages as 0. And then this TF unsorted segment sum can then sum up the attentional weights here. Attentional weights here, you can sum up all the indices 0, and then you can get your attention score sum, which is basically like, if for all the target paper 0, we can sum up all the attentional weights to be like, maybe like sum up all the values here to be maybe like 1.5. And then like, if let's say your target paper is 1, you can maybe sum up all the connections and you get like 1.2. So it's quite cool because with just one line like that, you actually do a for loop. The for loop is for, okay, maybe I write it down here. Like you're actually doing this for.
I mean, Chongmin, is this just like a computational trick?
Yeah, correct.
Or is it like something?
It's a computational trick.
Okay. Yeah.
You can also do a for loop for this.
Yeah.
Yeah. So I actually spent 3 hours trying to understand this code. So I wrote a lot of comments so that you can understand this better. Okay, because it really looks very difficult to understand actually. Yeah, without actually, because I actually did some experiments over it. You can see some of the experiments I did here just to show you how it works. Okay, so I'm just explaining to you how this works roughly. Okay, so the idea is quite cool. You take the sum of, based on the target node, you take the sum of the attentional weights. Okay, after that, what we do, we do a binary count of how many of these edges there are based on this source node. Like in this case, the target node 0 has 3 edges. Okay, then what we do is very, very cool. What we do is we will then imagine this is your original matrix, right? 1.5, 1.2, maybe 1.0. So it's like this corresponds to target node 0, target node 1, target node 2. But then we also take basically a node count. Okay, so we find out that maybe target node 0 gets repeated 3 times, target node 1 gets repeated like 1 time, and maybe target node 2 gets repeated 1 time, which means like there's only like 3 edges, 1 edge. So we can then expand this out into like that 1.5, 1.5, 1.5. So you can actually get the sum, okay, of whatever you get over here, you repeat out by the number of edges here. Okay, and then over here, you can then later divide by the attention score, because your attention score is over the entire thing. So my attention score will be like, for example, 0.5, 0.7, 0.3. So your attention score itself is already like classified by the nodes. So you can see that if you were to do a repeat like this, can you see the beauty of this? Later, when you do a division here, it is exactly normalizing all this to be 1. Okay, so all these tricks are just to normalize the attention score to be 1 for the same target node. All your attention score will be 1. Okay, so this is just a computational trick to do this. You can also use a for loop, but this is much faster. Okay, so these connected nodes, I also have another connected node here. It's using the same trick to like divide these neighbor states by the number of nodes. This is like the GCN part. Okay, this is I implemented this myself. So this is, instead of using attention scores, I just do an average. Okay, this is exactly what this code is doing.
Chongmin,
Okay, so
can I just check with you? If you look at that line, attention scores norm, it's not using softmax. It's doing what I told you, just divide by the sum.
Oh no, but the softmax part is here. The softmax is where is it? Yeah, the softmax is here. So yeah, so if you omit this line, then it will just be averaging. But because you do exponential, then it's a softmax.
So you're already doing the
yeah, it's still part of softmax.
Got it. Okay, thanks.
Okay, so over here you can get an output here, and you see the output shape is 2708 100. Okay, what this means is that we basically get the hidden states of each node. You see there's 2708 nodes, right? And the hidden state is 100. So based on this message passing, we get a intermediate node here with 100 hidden states, and then this is basically the outcome of the message passing. So this is just one round of message passing. You need to call this function many times per layer. So we have also in this code, I'm not going to go through this, but this is multi-head graph attention. You do the same process 8 times. Okay, and what they do is they just concatenate the output together. Okay, of this process out here. So you have 8 different attentional matrices. Okay, then this is the main code for the graph attention network. Okay, so you can see this is quite complicated. So all these are the layers. So each layer is one multi-head graph attention. So the output for each layer will then be added up in a ResNet style. Okay, so as you pass through the layer, you add up the previous information plus the attention layer information. So you keep doing that, you'll eventually get the final hidden output over here, which you can then use, okay, to do the training step. So the training step, you do it under gradient tape here to get the gradients. And the training step is very simple. Okay, the training step is really just Okay, this is the forward paths where you pass it through the nodes and edges over here to get like this. So when you do this, you're actually doing this over here. Okay, so this basically does the graph neural network part. After that, in order to compute the loss, you just take the labels and the indices. Indices are your inputs and these labels are your outputs. So this output is actually for everything. You select the indices that you want and then you compare to the labels. So this is the training process. So the inputs, so this is the predicted output and this is the true output. Okay, and so you do this for the loss, you do the optimizer to train it, and then to predict, you do the same step. You just take the probabilities here. Okay, so we'll not be going through the rest. Okay, the main part of the code is really just this multi-head graph attention. Okay, and after that, we do the evaluation here. Okay, this is the sparse categorical cross entropy, similar to how we do classification. Okay, this part is not as important. So you can see that when we train this, we get, oh, wow, 79.2% accuracy. Okay, and that is using the original edges plus new edges. I added this new edges to include self-connections. Okay, if I don't put the self-connection, actually it does poorer. So I invite you all to experiment with this code. Okay, so what you can do is you can just uncomment this one and comment this one in order to try out, like, if let's say we only do the original citation link without doing the self link, how well does it work? This is like the second best. Okay, this is the best, and this is the worst. If you only have the self links, it doesn't have enough information. So let me just show you if I only use the self link. So you see over here, this is a GCN with 79.2%. If I were to take away the linkages between papers in the citation, okay, this will basically mean I'm not using any of the information of the linkages between each other. Okay, let's see how well the accuracy is. Okay, so that was 79.2 earlier. Now you see it's 31.5. So you can see that actually the linkages between the nodes itself actually do matter. Okay, so I think it's quite late already. Unfortunately, I don't have enough time to go more in depth. But if anything, feel free to ask me. Okay, I would like you all to just play around with this as well. Up here, I have created down here, I put a to-do also. Okay, you can actually change, okay, GCN. GAT is the attention network. The GAT performs the best, about 80%. Okay, but GCN around the same actually. Yeah. In this case, the attention doesn't really make a big difference. And then there's this unnormalized GCN, which I don't divide by the number of connections. This performs the worst. This is like about 60%. So actually normalizing actually helps quite a lot. So this unnormalized GCN is something like a CNN where you just sum up all the weights. So you can see that in a graph connection, you may want to normalize because the difference is like more than 10% accuracy. So just uncomment this and like comment this in order to run the different cells. Okay, so just do this if you're interested. So let's just take a look at one of the classifications, like over here. Example 1, probabilistic methods. It does quite well. Genetic networks, good. Theory, good. Neural networks, good. Good, because it predicts highest. Theory, good. Okay, but this is not as confident. Genetic algos, good. Wow, this is 100%. Neural networks, good. Algorithms, good. Yeah, so you can see that actually it predicts perfectly for this case. Okay, so it's just nice. The examples are great. Okay, but the overall accuracy is maybe about 70. Okay, this 31.5 was using only the self connections. Okay, if we put in the original edges, it's about 80% accuracy. Okay, so I will end here for today. Okay, any questions so far on the notebook?